This lecture we start with chapter 2 and we focus on section 2.1. 2.1 is about linear systems of linear equations. Systems of linear equations. What do we mean by system of linear equations? By system we mean more than one equation that can be solved simultaneously. We just cover section 2.1 in this lecture, and next time we start 2.2. So if we have a linear function, that linear function can be graphed as a line. So it can be presented in the Cartesian coordinates as a line. Let's call it L1. And if we have, for the second equation, we may have L2. Let's call it L2. And now we want to see how the graphs look like. Since we are solving simultaneously, we want to see how the graphs look like. We have one of three cases. Either L1 and L2 meet in one point, and that means we have one solution, or those meet all the time. I mean everywhere. So they coincide. This is L1, this is L2, or vice versa. So they meet everywhere. So we have infinitely many solutions. And as you may remember from college algebra, by solution we mean the point where the two lines meet each other. And here, for example, for the first case, they meet in one point. For the second case, they meet everywhere. So there are infinitely many points or infinitely many solutions. And the third case is when the two lines cannot meet at any point. So they cannot meet, and meaning that there is no solution, because the lines are parallel to each other, and we usually use this notation to mean parallel to each other. Okay, so these are the three cases. Now we'll deal with solving systems of linear equations algebraically. So we don't need to represent them by graphing them. I mean, we don't focus on graphing those equations or functions and then find the points of intersection. The methods that we already dealt with, I mean in other math courses, are basically the elimination method and the substitution method. Those are very important and very powerful techniques and methods that can help us to solve linear equations. So let's start with the first system. For the first system, we want to determine whether this system has only one solution, or infinitely many solutions, or no solution. So let's solve this system by substitution. I'm going to solve it using substitution method. So this is the first equation, this is the second equation. Let's name them 1 and 2, and then we use substitution method. For substitution method, we solve for one of the variables, and as you can see from the first equation, we can solve for x. So solve for x. X gives 3y minus 9. And let's call this new equation star. This is an auxiliary equation that can be plugged into the other equation. If we get this from this equation star from the first equation, we can't substitute it back into the first equation. We need to plug it into this other equation. Now we plug this into the equation 2. We get 4x. Equation 2 becomes 4x, but x is 3y minus 9, plus 3y equals 24. Now we have an equation with one variable y. So let's simplify. 4 times 3y is 12y. 4 times -9, -36, plus 3y equals 24. And then 12y, 3y, that's 15y, minus 36 equals 24. And then we add the 36 to both sides to get 15 equals 60. And then we divide, 15y. Then we divide both sides by 15 to get y equals 4. Now after finding y, we just plug into the star equation to find x. X is 3 times y, 3 times 4 minus 9, and that's 12 minus 9, which is equal to 3. So the solution is x equals 3 and y equals 4. This is the solution. Now if we want to check our answer, we just plug into those equations that form the system, and we see if they are satisfied, if this point satisfies the system. So this is x, this is y. We plug x equals 3 minus 3 times y. We want to see, is this equal to the right hand side, -9? 3 minus 12 is -9, so those are equal. So the first equation is satisfied. Let's see the second equation. 4 times x plus 3 times y, is it equal to 24? We see 12 plus 12 is equal to 24. That means this is correct answer. This is how we check our solution. So we only have one solution in this case. So one solution. So x, y, this ordered pair is considered as one solution. Now let's do problem 2. I'm gonna erase this part to get more space to solve the second problem. Now for the second problem, let's use elimination method. We need to determine whether to eliminate x or y. As you can see, we can multiply by -4. Multiply the first equation by -4. And see what, if we can eliminate x or y. If we multiply by -4, we get -8x, and then we add it to 8x, and that gives a 0. That means by multiplying by -4, we eliminate the variable x. So the first equation becomes -8x. We multiply each term by -4. And the second equation is still the same. Then we add. So after adding those, this is 0, but this is 0 as well. And on the right hand side we have 28. So 0 equals 28. Is that correct or true statement? No, this is not a true statement. If we get a statement that's not a true, like 0 equals 28, that's impossible, then we say that there is no solution, meaning that the two lines are parallel to each other. So no solution. Now let's do the third problem. For this problem, we can solve it by either elimination or substitution method, but maybe elimination is easier because we have coefficients other than 1 here, so it's not easy to solve for x or for y, then plug it into the other equation. So let's use elimination method. I'm gonna multiply the first equation by -2 to eliminate x. So this gives us -10x plus 6y equals -4. This is the first equation. The second equation is 10x minus 12y equals 4. And then we add them. This is 0. I multiplied this as well by -2, so this should be 12y. And this is 0. On the right hand side we have -4 plus 4, that's 0. So 0 equals 0. This is true. This is true statement, but this is true for any value. For example, if we choose any value of x, any value of y, this statement will still true. If we multiply by 2, we get same answer. We multiply by 3, we get same answer. We have infinitely many solutions. So those meet everywhere infinitely many solutions. So if we see or we get a statement like 0 equals 0, 1 equals 1, something like that, that means we have infinitely many solutions and the two lines coincide. And that's correct, because if you look at the system, the original system, look at the equations here. If we multiply the second equation by 2, and that's possible, that's okay, we get this equation, but this is nothing but the first equation. This is exactly same as the first equation, and that means the two lines are the same. That's why we have infinitely many solutions. Now for problem 2, we want to determine the value of k for which the system, the following system, has no solutions. If you remember from the previous cases, no solution can happen when we get, for example, 0 on the left hand side and some number other than 0 from the right hand side. So let's do this. We want to show to find k that makes the solution has no solutions. That means the left hand side is equal to 0. So we multiply the first equation by -3 to eliminate x. So the first equation becomes -6x plus 3y when we multiply -y by -3 equals -6. The second equation stay the same, and then we add, so this is 0. Okay, so sorry. And the second part is 3y plus ky equals the right hand side is 1, -6 plus 7. But we want to find the value of k that makes this that makes the left hand side equal to 0. So we have y times 3 plus k equals 1. So we can take y as a common factor. And what is the value of k that makes the left hand side equal to 0? K equals -3. So when k equals -3, the left hand side is equal to 0, and we get 0 equals 1. That's impossible. So that means we have infinitely many solutions. Sorry, we have no solution for this equation. Let's do another problem. Now for problem B, same thing. We want to find the value of k that gives infinitely many solutions. Infinitely many solutions can happen when we have the left hand side equal the right hand side, and in many cases we get 0 equals 0. So let's try to get that. If we multiply the second equation by -2 to eliminate x, this is equation 1, this is equation 2, we get 2x plus 3y equals 6. This is the first equation, and the second equation becomes -2x -2ky equals -6. And then we add them. This is 0. Now the second part is 3y minus 2ky equals, the right hand side is 0. Now we can take y as a common factor. We get 3 minus 2k equals 0. Now this can be equal to 0. The left hand side is 0 because we want the left hand side to be equal to the right hand side. So we want this to be equal to this, because if the left hand side is equal to the right hand side, we have infinitely many solutions. Now this can be equal to 0 if this expression is equal to 0. So 3 minus 2k equals 0, and then we add 2k to both sides to solve for k, and we get 3 equals 2k, and then last step is to divide by the coefficient of k. So we get 3 halves. So when k is 3 halves, we get an answer like 0 equals 0, and then that means we have infinitely many solutions. Now how to formulate linear systems. Here in this problem 3, we want to formulate, but we don't want to solve. So the Johnson farm has 500 acres of land allotted for cultivating corn and wheat. The cost of cultivating corn and wheat is $40 for corn, $32 for wheat. Jacob Johnson has $16,800 available for cultivating these crops. If he wishes to use all the allotted land and his entire budget for cultivating these two crops, how many acres of each crop should be planted? Now here we let X be the number of acres of corn, and Y we need to define the variables. Y is number of acres of wheat. So we have X number of acres of corn plus number of acres of wheat should cover the whole area. The area is 500 acres. So this is the first equation. We need another equation. So for the second equation, we focus on the cost. So $40 for X, which is related to corn, number of acres of corn, plus 32Y is equal to what? The budget. The budget is 16,800. This is the second equation. So we got a system of linear equations. We call them linear equation because, as you can see, the power of the variables should be equal to 1, and when we graph them we get lines. Now another problem, we want to formulate but we don't want to solve the following problem. Manufacturer of women's blouses makes 3 types of blouses: sleeveless, short sleeve, and long sleeve. So this indicates that we deal with 3 variables, and here the time in minutes or in hours, let's use hours, required by each department to produce a dozen blouses of each type is shown below. So for cutting department, we spent 7 hours to produce sleeveless, and we have a dozen of sleeveless, and 13 hours to produce short sleeves, and 15 hours to produce long sleeves. And actually here we can define the variables. X, Y, and Z are defined as amount of sleeves. This is X. Y is amount of short sleeve, and Z is amount of long sleeve. So we can formulate equations. So let's start with the first line here. On cutting department, we have 7 sleeveless plus 13 for short sleeve plus 15 for long sleeve is equal to 80, because the available maximum of 80 labor hours. So we have 80 here in the first department, cutting department, and we have 22x plus 24y plus 29z is equal to how many hours are available for sewing. We have 160 in sewing department, and we have 6x plus 7y plus 7z. The maximum time available is 48. So we formulated a linear system of equations which involves 3 variables.